All right, question 5 is the acidity question, and I wanted to be a little bit forceful on how I said this in the question itself, in that I don't want just the definition of acidity returned to me. pKa is a measure of acidity, so it is a result of something being more acidic, not a reason why. So the why part is going to be structural. Now, your book talks about what's called ARIO, for atom, resonance, induction, and orbital. There's a little bit of confusion on that, so I want to clear that up real quick. Yes, it always applies, but there are some limitations. When we talk about the orbital, meaning the hybridization of the atom where the hydrogen was attached, in all of these cases, that's identical. So the orbital part of this, and all these cases, the hydrogen in question is attached to an oxygen. So both the atom and the orbital part of this are identical for all three structures. The oxygen is sp3. It has the same two lone pairs of electrons. So what I'm left with is only the things that happen outside of that, which means the attachment. Those are limited to induction and resonance. Now, whenever you start seeing aromatic rings or double bonds or groups with pi bonds in them, resonance should be in the back of your mind just as a possibility. And here you can see it is obviously going to be part of the explanation, because there's no other difference between the first and second structure. It's just that I have multiple bonds. So when we talk about the acidity, we want to be really looking at the structural stability of the conjugate base. A stronger acid gives a weaker base, better stated as a more stable conjugate base. So if we look at that, we've got the cyclohexyl version, which has basically nothing to help it. That charge is 100% localized. There's nothing to work with there. So this is our reference point. The others we're going to be comparing to that, because obviously we're going to have something going on with those, or they wouldn't have different values for the pKa values. So for the second one, well, based on what we just did in the previous question, we can start thinking, all right, we're going to use resonance in the aromatic system. And we do. We can actually draw four resonance structures, or 3 additional resonance structures from what I have there. From the original conjugate base structure here. And that's going to be involving this. And then we only need to draw one more of them for our explanation here. There's another one on the other side that's identical to this one, where that charge will be up here. But the one that's not identical has the charge opposite to where the oxygen is. That one's important because we're going to need that to explain the next one. So the difference here is we're introducing resonance. And what that does is drop the pKa by about 10 points. Remember, this is a logarithmic scale. So this, 7 points. This is 10 to the 7th times more acidic. So that is a massive effect. And then we're dropping down another almost 3 points to get to here. So this is roughly 1,000 times more acidic than the center one. Nitrophenol is that much more acidic. So the reason why is very similar. Is if we look at the nitrophenol conjugate base, we're going to have a similar setup to begin with, only we're going to get to that last resonance structure that I saw for phenol, the one at the bottom here. Resonance into the ring is going to be exactly the same. So that's not going to help me. If that were the only thing going on, those two values would be identical. But what will help me is that when I get to this last resonance structure here, where I've moved the negative charge to the other side of the ring, well, now look at where it ends up. It actually ends up right next to a cation. So I've got a negative charge on this carbon, and I've got a positive charge on the nitrogen right next to it. Opposite charges attract, even if they can't do anything with them, so that's beneficial. But we can actually do something with it. We can actually take that negative charge and resonate it into the nitro group and out the other side of this oxygen. So there's an additional resonance structure here, which involves resonance into the nitrogen. It's not possible for the previous examples. So I have this now, where I have a double bonded nitrogen and two singly bonded oxygens that are both anionic attached to it. The cation is still there. It doesn't change here. So I haven't created additional charged atoms. I originally had a negative charge on the conjugate base oxygen and the cation and anion that are always part of a nitro group. The nitrogen's always positive because it can't form more than 4 bonds. So to get an octet rule obeying structure, it means I have a positive charge on the nitrogen. One of the 2 oxygens is negatively charged, and that is resonating on its own all the time. That doesn't help us explain anything. This last resonance structure, and even the one before it that just moves a negative charge next to a positive one, help us explain why this is 1,000 times more stable than the one before it, meaning the acid is 1,000 times better acid than phenol, which in turn was 10 to the 7th, 10 million times more acidic than cyclohexanol. So resonance is a big part of that. I will say this, and I may have said it already in a previous video lecture, but I'll say it again. As one of my students pointed out to me that some of the default answers to any question that I used to ask in class were resonance, electronegativity, and no. And this is a person who had me for 2 semesters back to back. So if that's one of the things that comes up that often, that people think it's a default answer, maybe it's mildly important. Yes, electronegativity is important. Apparently, I'm a big fan of being negative when it comes to yes-no questions, so the answer is always no. But resonance is that important, and you're seeing the effect of it here. Just one effect of it. But the idea is that it helps you to stabilize charges no matter the context. If it's possible to do resonance, that's going to help. So this is a critical part of understanding things as we go forward.